Hello, and welcome to the MATS crash course. So, I'm Henry. I'll be taking the material science half of this crash course, and I'm not sure if Duda already went or is going after myself. But yeah, so Duda will be taking the chemistry half. So, here are my notes. I basically made two large documents of notes. One is for the stuff you need to know for the midterm, for material science, and then the other one is for the finals. Let me show you that one. Finals. Let's go to the top. Yeah, all that stuff over here on the left, right? Anyway, so if you want a copy of these notes, I've made a link tree. So that's linktr.ee/sigma lectures. And that has like a bunch of my notes on it. It has the Eng 1300 Bible, which I just updated. It has my YouTube channel. And here at the very bottom, it has the Google Drive for material science. So if you click that, it'll bring you to this link here. And yeah, so much else to say about that. I guess the main documents you want to be looking for is midterm cram and finals cram. Yeah, these stuff down here is just, they all ended up being combined into these documents basically. So yeah. Okay, okay, good. It's working. So we'll start with the midterm stuff, or the stuff in the first half of the course for material science. So that's on the left here. Oh, cool. Okay, so firstly, yeah, we'll do a little introduction as to what this subject's about. And then, I don't know, they talk about like atoms and stuff like that. To be honest, I don't really focus on this. Yeah, it's just like context, to be honest. This stuff kind of relates more to the chemistry half, which is also to do with atoms. In fact, in the first like week or two, you'll actually get mixed up between material science and chemistry, because like, honestly, yeah, they pack a lot of chemistry into these topics, which is not really my strong suit. Yeah, but then starting from the second half of week 2, we dive into elastic modulus, and this is where you get into kind of like mechanics of solids, which is just like, it's kind of like engineering mechanics, but on a smaller scale, I guess. We're talking about solid materials and their properties, basically, which is really what this course is about. Yeah, and then we'll talk about yielding, dislocations, yeah, all this stuff. This, honestly, it's pretty useful to learn this course before you do solid mechanics, which is in your first term of your second year, if you're doing this, in your first year. Yeah, it gives you a lot of context behind what you learn in solid mechanics, and I can see why they introduced this course into the curriculum, even though, to be honest, it's really, really annoying, this course. Like, this course is one of like the most stupidly assessed courses, like in terms of, yeah, it's crazy contact hours, stupid assignments. Anyway, I digress. So let's get started. Oh my god. Okay, don't. If you see this, you're just gonna be really confused, and it's literally not even in English. Like, half this, you're gonna learn the entire Greek alphabet basically, at the end of this course. But yeah, don't worry, we'll come back to that. Okay, so material structure, right? Atomic bonding. Yeah, this is all just context. I don't really care about the chemistry too much. So there's like crystalline structures, polycrystalline, amorphous, all that stuff. And here's just some examples of some materials which fall under these material structure categories. Yeah, basically with material science, we essentially only really care about solid state materials. Like later we'll do a little bit of metallurgy, which is talking about like how metals behave in liquid form and stuff like that. But yeah, most of the material science part of this course focuses on solid state structures, solid state substances, or whatever. Yeah, and then there's 4 general material classes, right? So this is pretty important. Yeah, basically we have ceramics, metals, polymers, and composites, right? And I've just given some examples which really relate to civil engineering. So concrete, that's probably the most used building material in the world. We also use like masonry, so like bricks and stuff like that, a lot. So steel is probably the second most used building material in the world. It's a lot more expensive, it's a lot denser, but it has really strong mechanical properties. It's also horrible for the environment to manufacture, but that's, you know, we love that kind of stuff as civil engineers. I'm just kidding. Yeah, and then timber is another pretty common building material. It's becoming more common with bigger buildings and stuff like that. I can yap on for ages about timber. It's what my thesis was about. But yeah, it's got really cool mechanical properties. We might touch on it a bit later. And then kind of like the weird, well, actually, to be honest, composites is quite strange in terms of its material structure. But polymers, yeah, they're quite unique as well. We do use this a little bit in civil engineering, but it's more so used. Oh, actually, yeah, we use epoxy a lot, you know, for like binding together boards of timber and stuff like that. But we can use carbon fiber. We can use stuff like glass fiber, to strengthen structures as well in civil engineering. We'll talk a bit more about these things more in depth later. I'm just trying to keep this yap under an hour or so. Yeah, just so you're not super bored. Okay, so in terms of bonding, there's a few different types of bonding. You'll learn this in the chemistry part. There's ionic bonds, covalent bonds, metallic bonds, and then they have these kind of properties, la-di-da. Yeah, who cares? And then the secondary bonding, which is kind of like, they're not directly bonded, but you have these kind of, I don't even know what these are. Okay, who cares? Yeah, whatever. Okay, let's go on to talk about Young's modulus and bond energy and things like that. So in terms of the actual atoms, right? So if you have two atoms, right, so for your material, like what is a bond? Like what constitutes as a bond? Well, essentially, yeah, the atoms, they're gonna be attracted through like electromagnetic gravitational forces and all that stuff. And there's kind of this graph which represents the energy required to maintain this bond. And there's kind of an ideal distance, which is called, we'll call that distance the R, right? And so yeah, there's an ideal distance which uses the least amount of energy possible, which is U min. So yeah, that's just like a general concept. And that's also the point which has the strongest attraction, right, in terms of attracting force. There's some sort of like relationship mathematically between bond energy, force, and stiffness when you derive it with respect to the radius. Yeah. Who cares? Shut up, bruh. Yeah. Oh, dislocation radius is kind of where the max slope is. And yeah, it's basically, sorry. Okay. Let me retract my previous statement. So basically, at the minimum energy, we don't have attraction or repulsion. So these atoms want to stay this set distance away from each other. But the dislocation radius is this point of maximum slope, and it's where you'll have like the max force wanting to pull it together as it's trying to break apart. Like these atoms are trying to pull apart. To dislocate this bond requires some amount of force, F max basically. Yeah. Okay, now we're moving on to elastic modulus. So this is less to do with that really small scale, like atomic scale. We're moving on to kind of, yeah, this applies to like macroscopic stuff. Yeah, like the cross section of a beam, or any kind of like rod or anything like that. Yeah, this is pretty important. So there exists a material curve, right, which you may or may not have seen. You might have definitely seen it if you did engineering studies in high school. It's basically where we graph stress and strain against each other. So if you've never seen this before, sigma is usually given an MPa, and it's this formulas for it. So basically, sigma is stress, And stress is a way of normalizing forces, right? So if you basically have, let's say, a rope, right? Let's say you have a rope and it's in tension, right? So this is being pulled apart. It's basically saying, okay, well, how much force do we need to break that rope, right? Well, you might be thinking, okay, well, it depends how thick that rope is, right? The diameter and that cross-sectional area, as a matter of fact, of that rope. And so we have to express how strong the rope is in terms of a stress, right? It has an allowable stress, right? And based on that stress and that cross-sectional area, we can figure out how much tension force will break that rope, essentially. We can backwork all these formulas. So I say here that the area is pi on 4 d squared. You might be more familiar with pi r squared. This is basically the area of a circle, but as you can imagine, if we have a cross-sectional area which is rectangular, like this, right? Yeah, this formula is different. Obviously, it's going to be whatever this side length is times by this side length, right? Yeah, okay, and then in terms of strain, right? So that was kind of to do with stress. Strain is a way of normalizing the displacement, right, of this rope. So let's think for a second about when we pull this rope, right? So going back to that rope example, how stretched it gets, right? That's what we call delta L. That's the change in length, or sometimes it's called the linear displacement. And we should normalize it based on this overall length, right? Because let's say this rope was 1 meter long, right? If we pull on that rope, it might stretch. Let's say it's 1 meter long. If we pull on that rope, it might stretch by 1 centimeter, right? Okay, cool. But, you know, if we have a rope of the same material and it's 2 meters long, right? You know, you'd expect it not to stretch by 1 centimeter. You'd expect it to stretch something like 2 centimeters. So we need to normalize this change in displacement based on the original length, and we call that strain, right? So strain is just delta L on LO. So you'd do 2 centimeters divided by 2 meters. You know, you'd convert it all to the same units, and strain ends up being unitless, right? So yeah, basically going back to the stress strain curve, right? This is sometimes called a material curve. Every material will have its own unique stress strain curve that kind of defines its properties as a response to external forces like pulling, like tension, for example, right? So yeah, for simplicity, I've called this notation here sigma as stress, right? But this is what we actually call the either axial stress, or sometimes you call it the normal stress, right? So if you have something like a rope, let's just say some generic mechanical member of some sort, right? We have different directions to define. So along this axis, right, which goes through its middle longitudinally, that is what we call the axial direction, right? And that's what we're doing. That's what all these formulas apply to, essentially, right? We'll get, I think later they touch on shear stress, which just works in a different direction. They also might talk about, no, I think it's just shear stresses. But anyway, yeah, okay, great. So yeah, this is the axial stress strain curve, essentially, that we've graphed. So this is just an example, right? So this, I guess, am I overcooking my explanation? Okay, maybe I'll come back to the shape of this particular curve, right? But it kind of looks like a parabola almost. There's this area which is relatively linear, like here. And then you have this area which falls off a little bit, right? So keep that in mind, we'll come back to it. So, yeah, there's a bunch of random ass formulas, and that's, if you remember the formula sheet I showed you earlier, you're gonna look at it and be like, why is there so many formulas? It's because we have a lot of empirical formulas, which are basically like based on testing or like approximations of what you'd expect for different materials. And because you know, I mentioned we have many different types of materials, you can, yeah, that's why there's so many different combinations of random formulas they can give you, essentially. So yeah, these are all approximate. These are all guesses for what what the yield strength is essentially. Okay, so let's talk about failure modes, right? So we have ductile, quasi-brittle, and brittle. Basically, the material curve I just showed you earlier, it looked something like this, right? Linear part and falls off, tapers off, a little bit like a parabola. Basically, this is what we constitute as a ductile material. Usually metals are ductile materials, right? So that's stress strain. What it says is that for the area which is linear, right? If we go back and forth in this area, as in we stress it, you know, say with the tension pulling force, and then we unload it and we stretch it and unload it, it's gonna not have any permanent deformation, right? So that's what we call elastic. That's what we call the elastic range. And if you think about an elastic band or a rubber band, right? When you stretch it and you unstretch it, it doesn't deform, right? That's why we call it an elastic band. But this area past here is called the plastic region, and that's where you start to get permanent deformation, right? So if you imagine something like Play-Doh, right? If you stretch it enough, it's gonna start. So here's a bit of Play-Doh. You start pulling it like this. It's gonna start. It's called necking, right? So that's where you have this permanent deformation. That's called the plastic region. And before it eventually breaks. So metals kind of behave like this, right? So steel beams and stuff, it has this kind of warning to tell you that it's about to break, essentially, because you can see there's this ductile behavior, we call it, or yielding, sometimes it's called. Whereas brittle materials, actually, rubber band's a good example. So a rubber band, it would have a stress strain curve. It looks more like that, right? It basically doesn't tell you before it's going to snap in terms of stretching, right? As in necking or anything like that, right? So rubber band, you stretch it enough, it stretches, and then it just snaps, right? It doesn't have any necking behavior like over here. Well, it has very, very negligible amounts, right? And there's a lot of materials that behave kind of like this. Oh boy. I'm going to stop my recording. Alright, sorry about that. Okay, continuing on. So that's basically the gist of brittle and ductile materials. Quasi-brittle materials, as you can imagine, they might have a material curve. It's all quite fucking subjective, but you have this linear part and then you have a little bit of tapering. That'd be something that's quasi-brittle. People say reinforced concrete, for example, is quasi-brittle. Yep. Depending on the amount of reinforcement, but yeah. Anyway. Okay. Ductility is measured in many different ways. People have different measurements of ductility. It's more so a vibe-based thing than anything. So people can agree that a material curve that looks like that is ductile. Something like that might be quasi-ductile, and then or quasi-brittle, and then this would be brittle, right? So then there's just different formulas. It expresses a percentage to tell you whether something is or isn't ductile. It's basically how much does it neck or whatever before it breaks, right? And there's different thresholds depending on who you ask, essentially. Okay, now we're moving on to dislocations, right? So essentially, dislocations are a part of metals, right? So dislocations is what causes metals to have their ductile properties. So here's what a metallic lattice looks like. And it's basically where you have deformations in this microscopic scale, right? They're called dislocations, essentially. And but for your ceramics, essentially it's difficult for this to happen. So ceramics are generally more brittle because this effect doesn't essentially happen on a microscopic scale, right? So your concrete and stuff like that, without any reinforcement, yeah, you're not going to essentially get any dislocations. It's just going to have more of a fast fracture breaking kind of failure mode. That's just a lot of word jargon, basically. Just trust me, bro. Okay, so there's something called defects, right? Which is essentially in your large scale, like metallic lattice or whatever, for example, there could be a misplaced atom, let's say, ion. Yeah, ion. There could be a misplaced ion, right? And if you have, yeah, there's different cases for them. You can give it a read through yourself. But yeah, if it's a single point, a single atom, it's called a point defect. And if you have a line of them, it's called a linear defect, right? And that's essentially what dislocations are. So they're defects on a kind of linear scale, I guess, right? There's some pictures of it here as well. There's a really good video by Efficient Engineer. You should definitely check out that channel. They cover a lot of material science concepts, and they have really good visualizations for it, essentially. But yeah, okay, yeah, there's some more like kind of mechanics of tiny atoms here. So as I mentioned before, there's stiffness, right? So that's the tendency for these atoms to want to pull apart, right? Yeah. What other stuff? Oh yeah, so when I say other moduli here, the one that we've been talking about, right, is E, which is the elastic, or Young's modulus, sometimes it's called. And as I mentioned, there is shear stresses as well as axial stresses. So this one's the axial stress one, and that's axial strain, right? Or normal stress, normal strain, right? So basically, your shear modulus is, I guess it just considers forces in a different kind of direction. So for example, let's get an example. Let's say you drop a cylinder. Oh no, that's not a good example. Do I have a good example? Okay, there's not really a easy example I can think of off the top of my head to explain this, but just trust me for now, bro. I think I have a picture of it later, maybe. Yeah, okay. So bulk modulus, this applies to fluids. So I know I said that the majority of this course focuses on solids in terms of the material science half. Bulk modulus actually does apply to solids as well, but to a very, very negligible scale. More so, it makes a huge difference for water and other fluids as well as gases. Makes the biggest impact. So it's to do with pressure, right? And it's essentially what causes, so if you imagine like a submarine or whatever, there's a high amount of pressure like underwater, and it causes that submarine to have compressive forces acting on it due to the water surrounding it, right? Yeah, so that's all to do with the bulk modulus. The Poisson's ratio is essentially the squash ratio. So if you imagine like a little slime or something, a slimy cube thing, a little bit of jelly, if I push down on it right against the ground, you can imagine it wants to stretch out in those directions. Like I'd say slime or whatever, or jelly cube, because it's going to be quite pronounced on like a slime or a jelly cube, right? But every material, right, every solid material is going to have this squash and stretch kind of ratio to it, right? Just to a lesser scale. This generally applies to soils, right? So if you're doing civil engineering, when you do soil mechanics, it'll definitely apply to that. Okay. Oh boy. So atomic packing, there's body-centered cubic, face-centered cubic, and close-packed hexagon. Yeah, whatever. Who fucking cares? You know what I mean? Yeah, you can just look through my notes. Okay, so strengthening, right? So this is more to do with mechanical properties now. Essentially, every material is going to have an intrinsic strength, right? But you can strengthen it based on your understanding of its like atomic structure. So for example, with metals, right? So we talk about steel a lot, but what you might not know is that steel is actually an alloy. of iron and carbon, right? So alloying, aka mixing a metal with a different type of substance, can actually improve its mechanical strength, right? That's just dissolving an impurity like carbon into its lattice, right? So another thing is work hardening. So work hardening is basically where you can, what's a good way to explain it? I guess like, yeah, it's basically when you give, when you stretch like a piece of metal, for example, a piece of steel, and we talked about that ductile kind of nature of it, all right, where it does that. This tapering effect is actually work hardening. It's due to work hardening. It's due to dislocations forming in the metallic. So this would be like a zoomed in piece of metal, right? So we zoom into that. You see these kind of like dislocations forming, and they actually start obstructing each other and from forming, right? And it actually, yeah, it ends up making the material tougher, right? So yeah, so what you can do is you can kind of like pre-stress a metal, right? You can pre-stress like steel, for example. You can load it past this elastic point and up until this point, for example, right? And then you unload it, right? So what we did was we slowly increased its stress up until this point, and now it's reached over here, and we can unload it like this. And when it returns, it follows the linear curve, right? And now, yeah, anyway, it essentially is going to be stronger, right? If you pre-stress it like that. It's going to be less tough because it's going to follow this material curve, but yeah, it'll be stronger. Okay, let's see. Grain size. Yeah, let's talk about that. So, should we talk about that? I guess an example of this would be if you have concrete, right? It's going to be made out of different size particles, right? So different rocks and stuff like that. And if you have smaller grains, right, it's going to take up more of this. It's going to fill up more of these kind of voids, right? And yeah, it's just going to have stronger mechanical properties and stuff like that. Yeah. Okay, so now we reached fatigue. So fatigue is quite an interesting concept. Cyclical loading just means loading and unloading. An example of this would be like a car, for example. So imagine a car tire. The parts of the rubber of the tire keep spinning around. It gets compressed when it when, say, for example, this part of the tire reaches the bottom or the ground, and it gets squashed, and then it gets unloaded a little bit here where it's not touching the ground anymore. Stuff like that, right? So fatigue is quite common in mechanical engineering, I want to say. Yeah, when you're dealing with machines and stuff like that. But in civil engineering, you can imagine like it could be to do with structures, right? So structures will experience loading and unloading of different amounts because, sometimes people will be inside a building, sometimes people will come out of the building, right? That's an example of cyclical loading, right? So there's all these formulas to do with it. So you can have basically there's two main failure criterion, right, for fatigue. So it can fail by having a high number of cycles, right? So let's just imagine this wheel thing again, right? A high number of cycles, but lowish stress, right? Or it can have a high amount of stress, right? But it's loaded less, right? So these are the two main ways it can break. Crack growth per cycle. Yeah, so basically cracks will start to form as you keep loading something and unloading it. So you imagine like a concrete structure, the cracks will keep growing and growing in size. Yeah, there's like basically formulas and stuff to do with it. Once something becomes cracked, right? You can't use stress anymore directly to express these formulas. You have to use something called the stress intensity, because stress intensity is proportional to the size of the crack, right? Okay. Yeah, it basically just does your head in. You have to like wrap your head around all these formulas, but they kind of make sense, I guess. Yeah. Yeah, here's like crack propagation. There's like all these formulas to do with it. There's all these questions I've included as well to do with it. Something that's quite interesting as well. So this is from the efficient engineer again. Basically, steel or some metals, right, can actually have an infinite fatigue life, right, which is one of its main, like in terms of durability, that's one of the best material advantages it has. So assuming that you don't, assuming that the stress that it experiences is low enough, you know, past like anywhere below this point here, it won't break down due to fatigue at all, right? It can have an theoretically infinite number of cycles. So ferrous materials is to do with like iron. So iron is Fe, the chemistry notation, right? So ferrous materials is materials based on iron, essentially, right? Like steel. Okay. Yeah, so there's some questions in your little like quizzes or whatever. Definitely in the midterm there'll be as well to do with fatigue. Again, next thing's fracture. So fracture can actually apply to ceramics as well as metals and stuff. So essentially the theory behind fractures is you have like a perfectly, you know, let's say like ideal material, right, of some amount of area or volume, and then if a crack forms in it for whatever reason, essentially it's going to grow due to further loading. So I'll give you an example. This is what we call like a tensile test piece. So it's where you pull this on either sides. I think this is one of your labs. You do a test on this specimen, right, which I think is made out of Pyrex or something. Yeah, you do your tests and it doesn't have any cracks in it. And then you record the results and stuff like that. But then you do another test where you have various sizes for cracks, and then you try to match that up with the theory and the formulas that they present here. And it's essentially saying that here's what the stress flow will look like. Yeah, like basically all the forces when you have cracks, or all the stresses, will have to concentrate and flow through these areas around the cracks, right? And it's actually one of the reasons why these test pieces are shaped the way they are. So they actually, I didn't do a very good job drawing them, but they actually look kind of like this, right? Because they want all the stresses to kind of like evenly flow through this area here. And also they're a bit more narrow in the middle here because you essentially want to encourage it to break here and not like here, for example. If you have a uniform force, like a tensile force pulling through it, it's very likely that it'll break here instead because it has a smaller cross-sectional area there, which will basically have higher stress than over here, even though the same force is flowing through it. Anyway, sorry, back to what I was saying. If the tensile test piece was like this instead, basically you're going to have these kind of points of weakness around the corners, which will experience an unusually high amount of stress, I guess, at those points. So it might snap off like here or something instead of the middle, right? Yeah. So there's all these stupid graphs and shit in this course that you have to like kind of work your way around. Yeah. Plastic zone radius yielding. Honestly, none of this is like super substantial, so I'm going to go through it quite quickly. Okay, toughness. So I've mentioned the word toughness a few times. Essentially, toughness is the integral of the material curve, right? AKA, it's the area underneath the material curve. So if you have a similar elastic modulus between a brittle and ductile material, I mean, unless the brittle material is like goes like that, right? You can imagine the ductile material is generally tougher, right? So yeah, you basically take the area underneath this graph, and that determines its toughness, right? Yes. La-di-da. Oh, another thing I should mention is that the yield stress is basically the point which it stops being linear, right? So for a brittle material, it doesn't yield, essentially. It just has one important point that we have to think about, and that's just its ultimate strength, aka the point at which it breaks. But for a ductile material like steel, its yielding point might be here instead, right? And that's like the area that's linear, and then it will also have an ultimate stress, which is much higher, or not much higher, is a bit higher, and that's like essentially the highest it can go for steel. Oh, okay, sorry. This diagram's a little bit better at explaining what I mean by when I said earlier about work hardening, right? So if you cold work steel, right, the CW steel there, you basically stress it to this point here and then unload it, and it makes it less tough, right? So it reduces its strain energy, but it actually has a higher yield strength. That's what I was trying to say, right? So the yield strength improves, so it doesn't yield at that same point anymore. But yeah, it will be less tough. So it basically becomes a bit more of a brittle material, which can be a good or a bad thing depending on its application. Yeah. So we also have creep mechanics. So creeping is basically strain rate, right? So if you remember this symbol from before, this is strain, and strain rate is just strain over time, essentially. So the strain over time can be a function of three different things: it's the stress, time, obviously, but also temperature, right? So temperature will affect how much something will strain over time. So strain is really important. Strain rate particularly is really important for, say you have a building and you put, we load the building with whatever, it might start to sag over time, right? So if you have like a beam or whatever, you can imagine how it deflects or deforms. It will start to sag more and more. So this is all to do with strain rate. So there's all these bloody numbers that you have to memorize because these are empirical formulas again. And then whatever, who cares? All right, that goes to the chemistry part. I have no idea how I'm doing for time, but I think I'm around 40 minutes. So let's see. Let's do the finals stuff. So that's everything you need to know for the midterm. So for the finals, let's try to go over this stuff. We'll kind of go over a bit quicker because it's not as important as what you'll learn. It's not as important until the finals, essentially, right? Okay. So phase diagrams. So phases are essentially kind of what I've been alluding to. So you have solids, liquids, and vapors, right? So vapors can be like gases and stuff like that. You also have so basically when you have something called a solution, it's where you have, let's say, a metal, and it's only in solid form, only in liquid form, or only in vapor form. But you can also have a mixture, and mixtures are defined as it can be more than one phase. So it can be like partially solid, it could be partially liquid as well, right? So there's a graph to do with pressure and temperature. La-di-da, shut up, bruh, who cares? Okay, so now we're kind of getting into metallurgy. Metallurgy is like essentially the science of alloying metals or making them stronger. Essentially, it's the science behind making steel, right? As one of its more important features, right? So yeah, we have something called a phase diagram. And then we have the concentration of carbon, right? So this is, we're looking at steel right now. So this is iron and carbon, right? So here on the left is pure iron. And then here we increase the amount of carbon. So I think somewhere around here is what we call mild steel. Maybe it's around here. And then we can have moderate steel, and then we can have, yeah, high carbon steel, essentially, right? Yeah, depending on what temperature we're at, or what temperature we cool it at, essentially the iron will heat up and turn into a slightly different, I don't know what the word is for it, these things, right? It turns into like austenite, ferrite, cementite, right? And these have different crystal structures and different properties and stuff like that. Yeah, there's all these stupid ass fucking equations. I don't like this subject very much, I'm sorry. I'm swearing more than usual. Okay, yeah, eutectic point. Oh, who cares? Yeah, so binary alloys are like where you mix only two types of substances together, so like iron and carbon. Tertiary alloys, as you can imagine, has 3, right? Yeah. So I've just listed a couple, yeah. This whole subject and this whole material science part is all just to do with like having a shallow but broad understanding of a lot of these different concepts. You don't really get too deep into anything because it's just a first year course. It's also trying to just get you exposed to a bunch of different ideas which are useful later. But honestly, they go into too much detail for some of these topics, which is just super unnecessary, like all the stupid formulas and stuff, right? So I don't remember some of this stuff, to be honest with you. Kinetics of phase change. So as you can imagine, you know, we have phases, we have like liquid, solids, gases. Phase changes is where you change between these states, right? And the kinetics is to do with the energy related to this, right? Yeah. Oh man, these formulas. I wonder what I can talk about. I don't know. This is all quite stupid. Okay, you know what? That's fine. Okay, so then they start talking about steels in general, and it goes from talking about it from literally like where it's mined, the different, I think these are called minerals, the different minerals that you find in steel, all the way into metallurgy and steel production and stuff like that, right? So yeah, here we're focusing on that phase diagram again. So instead of, the previous topic was to do with phase diagrams in general, but the phase diagram which you'll deal with the most is probably the steel one. Yeah, I've just included a bunch of stuff that you can read through. Honestly, it takes a while to read through all this stuff because it's just so dense with information. Yeah, I'll give some examples. Martensite, whatever, tempering steel, which are used for like making swords, I think. Pearlite, okay, cool. Okay, and then ceramics and glasses. So basically, they eventually in this course get really detailed into those different types of material classes. So the one that you just saw was metals, right, which they deal with quite in depth. And then they get into ceramics and glasses, right? And then later you'll see they also do polymers, and then they also do composites, right? Yeah. So an example of ceramics would be like concrete, right? Glass is actually slightly different. It has an amorphic structure, which means that it's kind of random like that. Whereas crystal structures are way more organized like this, right? Yeah. Yeah, literally talking about clay. Like what? Mechanical properties, yeah. Essentially glass has the lowest Young's modulus. Yeah, it has lower Young's modulus in general than metals, whereas other ceramics are generally higher, right? So if we compare all these things on a stress strain curve, glass would be something like that, and it's brittle. Metals would be something like this, but it's ductile, right? Which I don't even know if it's that strong, like that. And ceramics are generally like this or something. I don't know. Right? And we're talking about Young's modulus, like the slope, like that. Comparing all those things. Drew Minecraft pickaxe there. Yeah, hardness it's basically hardness is measured in terms of what can scratch something else. So generally talk about diamonds being able to scratch everything underneath it. Yeah, and then yeah, basically the hierarchy for hardness. Oh yeah, so this kind of goes back to fracture, crack propagation, things like that. It's actually quite important for ceramics, right? Because if you imagine, for example, if you just like have your bowl at home that's like ceramic and you drop it, right, from the same, say you have 100 ceramic bowls at home that look identical, right? They're all like IKEA bowls or something. You drop them from the same height. Some of them might break and some of them might not break. And the reason for that is because in the microstructure of this bowl, you might actually have cracks, right? And some of those cracks can propagate and yeah, just completely fracture the entire thing. And some can have less or different located cracks, right? So ceramics and their strength is actually inherently random, right? Yeah, these cracks are also called flaws or whatever. They're inherently random, and something that's part of the concrete course, right, in third year, it talks about the strength of concrete, right, which is again a ceramic material. Let's call its strength F, right? And sorry, let's put the strength on this axis, right? And then this is the probability of it being that strong, right? It is generally normally distributed like this, and this is the mean strength, right? Yeah, and it's actually random because of the locations of cracks and how many you have and stuff like that. And when you're designing concrete in civil engineering, you're designing for the 5th percentile value. You're essentially saying, okay, the nearly worst case scenario is what we're going to design for. We're going to assume that concrete, its strength is a little bit unreliable, and we're going to design it as if it's a little bit weaker than it actually is, right? So it's all to do with sample sizes, random distributions, stuff like that. But yeah, modulus of rupture is to do with bending strength, right? So it's that strength thing I talked about, but it's all to do with its strength in flexure. Yeah, there's something called the Weibull modulus, right? Which it's a little bit hard to wrap your head around because it's all to do with probability. Actually, it's a probability-based theory of materials, right? And it's saying that certain ceramics can be modeled using this kind of like bell curve shape, and the survival probability is given like this, right? And also, yeah, the probability of survival is 1 minus the probability of failure. So just make sure you check in your finals, whatever, that they're either talking about the probability of something surviving or the probability of failing. So going back to that example where I was talking about the bowls dropping, there's a chance that some of those bowls survive, and there's also a chance that some of those fail, right? And because of the axioms of probability and stuff like that, they're related to each other by the difference of 100%, right? So, yeah, the Weibull modulus M, right, is what they give everything in terms of. And then lower value of M means that it varies more, right? So here they give an example. Chalk is something that has a higher variance in its strength. Engineering ceramics like concrete might be something like that. Steel will be even higher. Steel is quite a reliable material. So even though we're talking about this in the context of ceramics, right? Yes, it does apply to other materials like steel, but it's less relevant for steel, I guess. It's still relevant, but it applies more in the context of like concrete and other ceramics, basically. Yeah, here I've drawn this isn't actually really part of This course is from concrete, but you can have a look at it if you're interested. It's to do with the normal distribution of concrete. Thermal shock. Oh yeah, it's to do with, I think they temper glass on your phone screen to make it more ductile, right? So you can actually make glass more ductile on like a phone, like a smartphone, or I think also like the protector case or whatever is tempered glass. Yeah, it just makes it better against cracking and makes it more ductile. Okay, polymers. So polymers are like plastics, I guess you can think of that as like the main one. But it's still like glues and stuff are made of polymers. Yeah. So essentially there's two broad classes of polymers. There's thermoplastics and thermosets, right? So generally thermoplastics, like polyethylene, are a bit weaker. They can be melted and reshaped if you heat it up to a certain temperature, right? But thermosets, essentially they're permanent, right? So epoxy, polyurethane, these kind of things. When you reheat it the second time, it's not going to cause it to be melted and reshaped, right? So it's like a permanent kind of plastic bond, right? It's all to do with the cross-linking in polymer chains, right? So I think in the first week you learned that polymers are in these kind of long chains and stuff like that. And then if you have multiple long chains of polymers, right, like this, sometimes you can have cross-linking between them, right, like that. And those are like actual bonds, not just like those secondary van der Waals bonds and all that crap. Yeah, so the more cross-linking you have, essentially the stronger your plastic material will be. Yeah, there's all these bloody examples, bro. Oh my days. Yeah, like this is just detail, is not super necessary. Time variation, it's kind of interesting. Yeah, there's also, yeah, you know how I said heating, remolding plastics and stuff like that. Temperature is a big part of these kind of polymers. Yeah, glassy regime, whatever. There's different stages to heating and all that crap. Okay, composites, right? So as I mentioned, timber is a composite material. Timber's quite cool, but another type of, probably the poster child of this topic, is fiber reinforced polymers, right? And you can have different types. You can have glass, glass fiber, carbon fiber, these kind of things, right? These are all structural materials. They can be used as structural materials. And essentially, when you have composite materials, you're taking different types from the other material classes, right? And you can use one as the reinforcement material. So as a reinforcement material, you can use glass fiber, or you can use like carbon or whatever. And then you have a matrix material, so like epoxy or like polyester, and they might look something like this, right? So you can see the fibers running longitudinally like this in this fiber reinforced polymer. And then basically the matrix material is the glue. It holds everything together. Yeah, Kevlar is an example. I think it's also called aramid. Kevlar is actually the aramid. Kevlar is a brand name, but it's what like bulletproof vests and stuff are made out of. It has like a high impact resistance and stuff like that. So there's really interesting properties when you combine what do you call it? Bloody hell, what am I saying? When you combine different materials and make composites, right? What is this? Oh yeah, there's heaps of interesting mechanical properties. Yeah, fiber direction matters, right? So you can imagine if you pull these kind of like fibers apart to the cross-sectional direction, they'll split much more easily, right? Than if you pull it longitudinally. So if you have your timber, right? So we talk about like grain direction in wood and stuff like that. So because wood is a composite material, right? Yeah, if we pull it that way, it's going to be much stronger. Or maybe not pull, let's say push together, right? it's going to be much stronger than if you push it together perpendicularly, because it'll cause the grains of wood to split, right? So you can think of composites like a bundle of straws, right? So the straws are like the fibers. And yeah, whatever kind of forces that you apply to this bundle of straws in whatever directions is essentially how you'd expect it to react. Young's modulus. Yeah, so the modulus will also have different properties depending on the direction, not only the strength, right? So yeah, it's really interesting. VF is the volume of fibers compared to the matrix material, right? So going back to this picture, if I had even more of these longitudinal kind of fibers per, let's say like per square area, compared to the matrix material, then then the portion of fibers increases, right? And the portion of matrix material decreases. Okay, that's pretty much it, I think. Is there another topic? Rule of mixtures. Yeah, this is all to do with composites. Oh, corrosion. I shouldn't even talk about corrosion. There's a lot of chemistry related to it. Basically, for things like, let's say, steel, steel can rust, right? So dry corrosion is rusting without water, so it's just exposure to air. And wet oxidation is where there's also water, like moisture in the air, which causes it to essentially rust faster. Yeah, this is probably the most, bloody hell, anodes, cathodes. This is probably the most chemistry that's in the material science half, to be honest. Oh my days. Hated this topic. Oh, wait, I'm getting into chemistry now. Okay, that concludes it. Alright, thank you for watching. I'm gonna end this.